Hi all, welcome to lecture 3. So we'll be formalizing an expression for a very powerful and basic criteria that is called the Neyman-Pearson criteria for detection. But before that, we need to set a context as to why it is important and how it is approached. For that specific reason, let's start with solving a problem. Okay. So we saw this problem multiple times, but now we'll be trying to calculate this. Okay, we'll be using our mathematical abilities to try to understand what it is. So you might remember this particular friend. I mean the picture. Coincidentally, the color of my shirt and the color of the graph, the shaded area comes out to be somewhat same. But anyway, uh, we have the hypothesis H naught as the null hypothesis where no signal is present. That means there is just a noise. We assume the distribution of noise to be Gaussian. And when we have the alternate hypothesis where we claim that the particular signal was present, that was the DC signal of amplitude 1, we have this. And because we are taking only one sample, we are representing it like this. Okay. Here what we have is we have defined the probability of false alarm to be 10 power minus 3. That means we have set a level of tolerance beyond which we won't be accepting the false alarm in our detector. Okay. So 10 power 3 means 1 in 1,000. So in 1,000 transmission, only in 1 we will be accommodating false alarm. Having this condition, with this constraint, can you tell me the maximum probability of this detection? Okay. Now, as we saw in the last lecture, that this particular threshold of 0.5, this is what we have chosen. Okay, and accordingly we have a P of FA, which is of course much bigger. Now, what we need to do is we need to shift this. We need to shift this particular threshold by some limit so that this area under the integration, this particular area we have, this is actually the P of FA that we discussed from the last class. This is very small. This is 1 in 1,000. The area should be 0.001. That is what we want. So we need to shift the detector from the threshold from 0.5 to that particular place. But what is that particular place? We don't know. We need to know what is that particular place. So let us assume that this is x is equal to gamma, because only when we know what is x is equal to gamma would we be able to calculate this particular region, which would be the probability of detection. Without calculating the threshold, we won't be able to get into that conclusion. Okay, so let's try with the expressions that I have already written down. This is what I have discussed in detail in the last lecture. We shall be starting with this particular expression. Okay, so probability of false alarm. Okay, what is that actually? That is when the hypothesis was null. Actually, under null hypothesis, when there was no signal sent, we detect a signal H1. We can also represent it by integrating from the region R1. So because we chose this threshold, this is the particular region R1. Now, what is this region R1? We have the hypothesis under H0. That means we have this particular, we need to have this particular curve as our function, as our probability function, because it's under this hypothesis that this P of FA works. So can we say that this is from gamma to infinity, that's the region R1, probability of x given H0, this particular hypothesis is a Gaussian, is a standard normal with the mean 0 and the variance 1. So can we write this as 1 by root 2 pi e power minus t square by 2 dt. Now you know that changing the variables in an integration like that does not change the expression for integration. It completely remains unchanged. Exploiting this, you could have kept it anything. It does not matter actually. What I want to say is this is a common expression for a function that is called as Q function in engineering. If you have come across, this is used very widely. Okay. So because this is particularly gamma, we have this Q function as Q of gamma. Now what we are given is Q of gamma is equal to 10 power minus 3. We are given this. Now just like there is a table for logarithm, there is a table for this Q function as well, from where you can find that gamma is equal to 3 if the q of gamma is 10 power minus 3. There is a table because the calculation gets a lot complex when you go into the squared power of an exponential. Okay, this is what we need to realize. Initially it was at 0.5, now it's at 0.3. So basically it's not even here, it's not even before 1, it's 2 units right to 1. So that means that the threshold that we have set by setting this probability of false alarm will be somewhere here. Okay, but there is a very small area under the curve which was 0.001, which we want. So see, the probability of detection that we will be getting will inevitably be very less here. Okay, now how to find that probability of detection? You see, just like PMIS, we can actually make the equation for probability of detection. What is probability of detection? It is when we have the hypothesis H1 under H1. So we can obviously write it as this particular area. Now this particular area will be from gamma to infinity, but we shall be taking this particular curve. Now this particular curve is under hypothesis H1, which is basically a standard normal Gaussian shifted by 1. The mean is shifted by 1. So we can write it as 1 by root 2 pi e power minus of t minus 1 whole square by 2 dg. Okay. Now this becomes q of basically gamma minus 1. Okay. Now gamma was equal to 3. This is what we have found. So q of gamma minus 1 is equal to q of 2. If you take out the table and if you try to check the value of q of 2, it will come out to be somewhat 0.023. That means that the probability of detection given this threshold is 2.3%. Okay, so this is very less. I mean, only 23 cases you would be able to detect properly if there are 1000 transmissions. So this is exactly what we don't want. Okay, so from this problem you can see there are two things. Firstly, we have the necessity to have an optimal detector in this scenario. Now to have an optimal detector, here is the catch. The more you slide this particular threshold, you can see that the probability of false alarm, the P of FA, where in 0.5 it was much more, it gradually reduces. Now when probability of false alarm reduces, the probability of detection also reduces. So to find an optimal detector, you cannot make probability of false alarm is equal to 0. It won't happen, although ideally we would be wanting so. It won't be happening. So we would need to sacrifice on the quality of the detector by having some tolerance on the probability of false alarm, because without that we won't be getting a detector at the first place. We would be having very inefficient detector. That's what this example signifies, and that's the problem we are going to tackle just with this Neyman-Pearson criteria. So why this Neyman-Pearson criteria? What does it talk about actually? So Neyman-Pearson criteria says that if we want to increase the power of an LRT or the likelihood ratio test, we don't need to know what an LRT is right now. You can just say that it's the power of a detector. Okay, so the detector would be defined by the probability of detection. This is the power we have seen in the last lecture. Now if you desire to increase the power, we also should accept the consequences of greater rate of false alarm. I mean the P of FA will also increase and we need to accept the consequences of it. Okay, so with power comes responsibility. Okay, you see, the ideal scenario would have been that we detect it with the optimal probability of 100% rate of detection and there is no false alarm. But in reality, this ideal limit is not reachable in most systems which are very complex, which are much more complex than the example that we are dealing with. This is simply not possible. We are bound to have some false alarm and correspondingly we are bound to have some probability of detection. What the Neyman-Pearson criteria is about, it's a mathematical expression where the goal is to maximize the detection probability where we have an upper bound of the false alarm. That means given a rate of tolerance, we want to maximize the probability of detection. Okay, this is our problem statement. Now we are going to solve this. Okay, so if we can see it in a like if we place a little more attention, we can see because it is bounded, we have a constraint here and we need to optimize a particular. So this is a constraint optimization problem. That is what we are going to make it to now. So because the upper bound of false alarm is set, let it be alpha. So we have P of false alarm minus alpha is equal to 0. Okay. We'll be assuming this to be a function. For example, this is equal to f of x. Now, what we assume is that what we want to optimize, the optimum value of g of x, that is PD, is when the constraint has a particular value, that is here it is 0. So to solve the constraint optimization problem, we can have a Lagrangian. Let us denote it by f, capital F, which is the constraint plus lambda times the function we want to find the optimum value of. You know this as a part of constraint optimization problem, right? Now we just want to rewrite this f of x and g of x in terms of PD and PF. This is what it is, because g of x was to be 0, and that is PFA minus of alpha, and we have the PD here. Now let's try to rewrite it in the integral expression. So PD, you know, that is under region R1. We detect when already the signal was sent. I'm sorry, this is not P, this will be X. So already the signal was sent plus lambda times we have R1. What is P of false alarm? That is in the region R1 when the signal was not sent but still it was detected. It is always detected in the region R1, but the signal was not sent, right? This is what I want you to be very thorough in. These are the concepts that I want you to be thorough in. You should be able to recall what PD, PMIS, PFA is just instantaneously. That's why so much of visualization. That's why I pushed so much of explanation and so much of visualization into this. Okay. So now it's just a matter of rearranging right now. Okay. Now just take all the integrals into one side. So we'll be having P of h1 dx plus lambda times P of h0 dx minus alpha and lambda. Now the lambda as a part of constraint optimization problem, we have this is greater than equal to 0. We don't need to bother about it at this outset at the moment. We'll be focusing on optimizing this. Okay, so what is our goal actually? If we want to optimize, if you want to find the optimal value, what is our goal? I want to decide what is R1, and the moment we decide what is R1, we know what is R0, because that's how we have designed the problem. This is a binary detection problem. Once we have the region R1, we also have the region R0. Okay. Now we decide a particular value of R1, the optimum one, and with that we try to optimize the value of F. Now in that particular criteria, to set a criteria for optimization, we assume that this particular value, see, this can either be positive or be negative. Okay, when this entire value P of x under h1, let's not put dx here, I'm sorry, here dx is a this mistakenly got into this, lambda P of x under the hypothesis h0. This particular expression, if it is greater than 0, then let's get it to R1. Okay, this is the optimization criteria that we have set, because this will decide the boundary of this problem. This entire function, if it is positive, then the area would gradually go into the positive segment, and if it is negative, the area will be going to negative. In that way we are trying to optimize it. This is the optimization criteria. For all those values of x, If this particular expression is greater than 0, then it goes to R1. Okay. Now just rewriting that, we would be getting, if we just rewrite, we would be getting x given h1, a probability of x given h0 that is greater than actually minus lambda. If that happens, then for this particular x, this all value of x that belongs to the region R1. Okay. Now this particular value we can actually rename it, because minus lambda does not seem very good. We can rename it as gamma. So this is the particular criteria that we have. This is the particular test that we set up. This particular expression that you have is called as the LRT, or the likelihood ratio test, because we are actually testing the ratio of two likelihoods for a particular value. There is a beautiful thing to note here. This particular threshold that we'll be having, the threshold gamma, how do you obtain that? We obtain that from P of FA, just as we have seen from the last example. P of FA would be giving us that particular value of threshold, and when this LRT, the value of this ratio, is greater than the threshold, then that particular observation belongs to the region R1, or else it belongs to the region R0. Now, when we have a constant signal in noise, the NP detector is the most powerful detector for this problem. Okay, this is a very interesting, there is a very rigorous proof of why this is the best detector when we have to detect a constant signal in noise, embedded in noise. We won't go there. This is just a side note. Okay. Now, to summarize the Neyman-Pearson criteria, what we actually have, our goal was to maximize the detection probability, and we had a upper bound of P of FA. Now this particular upper bound of P of FA actually gave us the value of the threshold that we'll be dealing with. Now for this particular value of threshold, we have set up this particular LRT by giving our criterion. Now this particular LRT, likelihood ratio test, given hypothesis H1 and given hypothesis H0. If it is greater than this threshold, this ratio, we throw it into the region H1, the hypothesis H1, and if it is less than H0, then we throw it under the hypothesis. I mean, it's less than gamma, the threshold, we throw it under the hypothesis H0. Okay, so this is our entire criteria. This is the Neyman-Pearson criteria. Simple but very elegant. Okay. How do we detect this particular gamma? This can be detected by the determined by the given limit, given tolerance of P of FA. Okay, because P of FA is basically when false alarm is a signal was not sent but it was detected, and the detected region is R1. So this is basically X such that the LRT is greater than gamma. Okay, P of X H0. Now when you actually have this particular value, when we have a value of P of FA, when we are given the tolerance, we can actually determine gamma from that. We'll be solving a lot of problems to show this. Okay, the threshold can be detected, this threshold gamma can be detected from the value of P of A that is given to us. Okay, now there is one more thing that I wish you to remember, because this will be important. Whether this particular likelihood or this particular likelihood, it does not matter, all of them. If this particular x, the variable that you have in both the numerator and denominator, if this belongs to r power n, if this is multi-dimensional, still the LRT will be single dimensional. Okay, so this particular LRT that we get is a single valued random variable. Okay, once again there is an elaborate proof for that which is not necessary to us at this instant. Okay, so there are some things to take from this lecture. Why do we need the Neyman-Pearson criteria? Because given an tolerance of P of FA, we have to find the optimal P of D that will be getting. So that optimality condition can be set up by the LRT, likelihood ratio test, the threshold which can be found out from the upper bound of the probability of false alarm that is given to us, and with the help of that we can decide a threshold for which we will be having the optimum value of the detection. Okay, so with this I want to end this lecture today. In the next lecture we shall be solving a few problems that would make this particular concept further, like give further clarity to this particular concept, because there is a possibility that the full scope of this particular test might not be appreciated when we just discuss the concept without discussing the problem. So that's exactly what we will do in the next lecture. Okay, thank you for listening. Please comment out any of your doubts. If you have any, I'd be happy to respond to all of them. Let's keep it here for today. Have a good day. Thank you.